You probably think light is just light. It illuminates objects so you can see them, travels at a definite speed through space, carries energy from the sun to Earth. This seems straightforward until you actually measure what light does under controlled conditions. Then light reveals a nature so contradictory that it forced physics to abandon one of the most basic assumptions about reality. Light behaves as a wave when we measure its wave properties, and as a particle when we measure its particle properties, but it never displays both natures simultaneously. The choice of measurement determines what light becomes, but physics cannot explain how light knows what we're measuring or why it should care what we want to find out about it. Richard Feynman understood this mystery better than almost anyone, not because he solved it, but because he was willing to accept how deeply strange the experimental evidence actually is. The wave-particle duality of light isn't a limitation of our measuring instruments or a temporary gap in theoretical understanding. It appears to be a fundamental feature of reality itself. Nature refuses to have definite properties until observation forces it to choose which properties to exhibit. But this conclusion leads to questions about the relationship between consciousness and physical reality that science cannot begin to answer. The story begins with something that should be simple. Shine light through a narrow slit onto a screen, and you see a pattern of bright and dark bands, an interference pattern that can only result from waves overlapping and canceling each other. Light is clearly behaving as a wave, spreading out as it passes through the slit and interfering with itself to create the alternating bands. This wave behavior explains how light bends around obstacles, how it refracts when passing through glass, how it creates the colors in soap bubbles and oil slicks. The mathematical description of light as an electromagnetic wave works with extraordinary precision for countless optical phenomena. But when you try to detect individual units of this light, everything changes. Point a sensitive detector at the light beam, and you discover that light arrives in discrete packets called photons. Each photon carries a specific amount of energy that depends on the light's frequency, and photons arrive at the detector one at a time as distinct, indivisible units. There's no such thing as half a photon or a fraction of the minimum energy quantum. Light is clearly behaving as particle-minus discrete objects with definite energy values that can be counted individually. This particle behavior explains the photoelectric effect, how solar cells convert light to electricity, how photomultiplier tubes detect individual photons. But photon detection seems to contradict everything the wave model predicts about light's behavior. The contradiction becomes acute when you combine both types of measurement in a single experiment. Set up the classic double-slit experiment, with light dim enough that only one photon passes through at a time. Each individual photon hits the detector screen at a specific location, creating a single dot just like a particle should. But as you accumulate hits from many individual photons, the dots arrange themselves into the wave interference pattern, alternating bands of many hits, and few hits that can only form if each photon somehow passes through both slits simultaneously and interferes with itself. Individual photons are behaving as particles when detected, but collectively they're exhibiting wave interference that requires each photon to take multiple paths through the apparatus. But this seems impossible if photons are discrete particles with definite trajectories. Install detectors at the slits to determine which path each photon actually takes, and the interference pattern disappears. Now photons behave like classical particle. Each one goes through one slit or the other, never both, and they arrange themselves randomly on the detector screen with no interference pattern. The wave behavior vanishes the moment you try to observe it directly, but remove the path detectors, and the wave interference returns immediately. Light switches between wave and particle behavior, depending on whether you're measuring which path information, but there's no physical mechanism that explains how light knows what you're measuring or why it should respond to your choice of experiment. This isn't about the clumsiness of measurement disturbing delicate quantum systems. Physicists have devised ever more sophisticated experiments to minimize the impact of measurement on light's behavior. They've used quantum non-demolition measurements that extract information without transferring energy, delayed choice experiments where the decision to measure wave or particle properties is made after the photon has already passed through the experimental apparatus, and quantum eraser experiments where path information is gained and then destroyed before detection. In every case, light's behavior correlates with what information is available about its properties, not with any physical disturbance caused by the measurement process. Light seems to be responding to the availability of information rather than to mechanical interactions with measuring devices. Perhaps the most disturbing aspect of wave-particle duality is how it suggests that light doesn't have definite properties when it's not being observed. Between emission and detection, a photon exists in what physicists call a superposition state, a quantum combination of all possible wave and particle properties that doesn't correspond to either waves or particles as classically understood. The photon isn't traveling as a wave that will later be detected as a particle, nor is it traveling as a particle that happens to exhibit wave-like interference. It's traveling in a state that has the potential to manifest as either waves or particles depending on how it's eventually measured, but it doesn't manifest as either until measurement actually occurs. But this interpretation implies that physical properties don't exist independently of observation, which violates every intuition about how reality should work. The mathematical formalism of quantum mechanics provides extraordinarily precise predictions about light's behavior in any given experimental setup. You can calculate exactly where the bright and dark bands will appear in interference patterns, predict precisely the probability of detecting photons at any location on a screen, determine with incredible accuracy how changing the experimental parameters will affect the results. But the mathematics describes probabilities rather than definite outcomes, and it treats wave and particle properties as complementary aspects of a more fundamental quantum reality that has no classical analog. The equations work perfectly, but they don't tell you what light actually is. They only tell you what you'll observe when you measure it in various ways. Feynman was particularly troubled by attempts to visualize what's really happening in quantum systems like light. He understood that the human mind evolved to comprehend a classical world where objects have definite properties and follow definite trajectories through space and time. Quantum mechanics asks us to accept that light exists in superposition states that combine wave and particle properties in ways that cannot be visualized or understood through classical concepts. We can learn to use the mathematics effectively, but we cannot form mental pictures of what the mathematics describes. Light's true nature, if it has one, exists beyond the reach of human visualization, and perhaps beyond the reach of human comprehension. This limitation extends to every attempt to explain wave-particle duality through analogies or metaphors. Light isn't like a wave and a particle simultaneously. It's something fundamentally different that exhibits wave-like properties under certain measurement conditions, and particle-like properties under other measurement conditions. The wave and particle descriptions are both approximations that capture different aspects of light's behavior, but neither one represents what light actually is in itself. There may be no deeper reality beneath the quantum mechanical description, no hidden layer of explanation that would make wave-particle duality feel intuitive or reasonable. The strange behavior might simply be how light actually works, without any further explanation being possible or necessary. The technological implications of wave-particle duality surround us in ways most people never consider. Lasers depend on the quantum nature of light emission and the wave properties that allow coherent beam formation. Solar panels convert photons into electrical current through photoelectric effects that require light's particle nature. Fiber optic communications rely on light's wave properties for transmission and its particle properties for detection. Quantum cryptography uses individual photons to create unbreakable codes. Medical imaging techniques from X-rays to MRI scanners exploit different aspects of electromagnetic radiation's dual nature. The modern world runs on technologies that work because we've learned to harness light's quantum properties, even though we don't understand why light has these properties. But the technological success doesn't resolve the conceptual mystery. Every practical application of wave-particle duality requires choosing to measure either wave properties or particle properties, never both simultaneously. We've learned to predict which aspect of light will manifest under different circumstances, but we haven't learned what determines this manifestation or what light is doing when we're not measuring it. The technologies work because the mathematics of quantum mechanics works, but the mathematics describes rather than explains. We can use light's dual nature effectively without understanding what that dual nature actually means. The mystery deepens when you consider that wave-particle duality isn't limited to light. Every quantum particle, electrons, protons, neutrons, even large molecules exhibits the same complementary behavior. Matter particles show interference patterns when their wave properties are measured, and behave like discrete objects when their particle properties are measured. The entire microscopic world appears to exist in quantum superposition, until measurement forces it to manifest definite classical properties. But if everything is quantum mechanical at the fundamental level, why does the macroscopic world appear so classical and definite? This is where the explanations become even more puzzling. The transition from quantum superposition to classical definiteness seems to occur through a process called decoherence, where interactions with the environment cause quantum systems to lose their wave-like coherence and behave more like classical particles. But decoherence doesn't actually solve the measurement problem. I know, it only explains why quantum effects become difficult to observe in large, complex systems. The fundamental questions about what causes wave function collapse and why observation should have special significance in determining physical properties remain unanswered. Light still doesn't know what it is, and decoherence doesn't explain how it decides what to become. Recent experiments in quantum optics have pushed the boundaries of wave-particle duality in ways that reveal even stranger aspects of light's behavior. Scientists have created single photon states that exist in superposition between different numbers of photons, states that are simultaneously one photon and no photons until measured. They've demonstrated quantum entanglement between photons separated by vast distances, showing that measuring one photon's properties instantaneously affects the properties available to measurement in other photons, regardless of the spatial separation. They've created photon states that violate classical logic by exhibiting properties that seem mutually contradictory according to any reasonable understanding of how things should behave. But these experiments only deepen the mystery by showing that light's quantum nature is even stranger than the simple wave-particle duality suggests. Perhaps most unsettling is the role that consciousness seems to play in determining light's properties. The switch between wave and particle behavior correlates with whether information about light's properties is available to conscious observers, not just with whether measurement apparatus is present. Experiments where path information is recorded but never looked at by humans still destroy interference patterns. Experiments where path information is erased before human observation can restore interference effects. Light appears to be responding to the potential for conscious observation rather than to the mechanical details of measurement apparatus. But physics provides no framework for understanding how consciousness could influence fundamental physical processes, or why the universe should care whether humans know about the properties of light. This suggests that consciousness might not be merely observing physical reality, but participating in creating it through the act of measurement. The classical picture of science assumes that reality exists independently, and that consciousness simply discovers facts about that independent reality. Wave-particle duality suggests that consciousness and reality are more intimately connected. That the properties we measure might not exist before measurement creates them. But this conclusion leads to philosophical questions about the nature of consciousness, observation, and physical reality that lie well beyond what experimental physics can address. We can measure the correlations between consciousness and quantum behavior, but we cannot explain why these correlations exist. The implications extend to our understanding of the universe itself. If wave-particle duality is fundamental to all matter and energy, then the entire cosmos exists in quantum superposition until observation forces it to manifest definite properties. The stars you see in the night sky might not have definite positions and brightness values until the light they emitted billions of years ago finally reaches your eyes and is measured by your consciousness. The history of the universe might be created retroactively through observations made in the present, with quantum effects propagating backward through time to determine what actually happened in the past. But these possibilities push quantum mechanics into domains where it becomes impossible to test experimentally or even to think about clearly. Feynman's approach to the wave-particle duality was characteristically pragmatic. Rather than trying to force light into classical categories or construct elaborate explanations for its quantum behavior, he advocated accepting the experimental evidence and learning to work effectively with quantum mechanics regardless of whether it made intuitive sense. The mathematics of quantum electrodynamics, the quantum field theory that describes light and its interactions with matter, is the most precisely tested theory in the history of science. It predicts experimental results with accuracy that exceeds 1 part in a trillion in some cases. But this extraordinary precision comes from describing rather than explaining quantum phenomena. The theory works perfectly without telling us what light actually is or why it exhibits wave-particle duality. This pragmatic approach has enabled incredible technological advances and scientific discoveries, but it leaves the fundamental questions about light's nature completely unresolved. We've learned to calculate when light will behave as waves and when it will behave as particles, but we haven't learned why it should have this dual nature or what determines which aspect we observe in any given measurement. The mystery remains as deep today as it was when quantum mechanics was first discovered, despite decades of increasingly sophisticated experiments and theoretical developments. Light continues to refuse classification into any category that makes sense according to classical intuitions about how things should work. Perhaps the most remarkable aspect of wave-particle duality is how it continues to function perfectly despite being incomprehensible to human reasoning. Every laser, every solar panel, every fiber optic cable, every quantum computer relies on light's dual nature working exactly as quantum mechanics predicts. The phenomenon that seems most mysterious and counterintuitive has become the foundation for technologies that define the modern world. We use light's wave-particle duality constantly without understanding it, harness its power without explaining its origin, and build our civilization on principles that violate every expectation about how reality should behave. The wave-particle duality of light might represent a fundamental limit to human understanding of physical reality. We can describe quantum behavior mathematically, predict it experimentally, and use it technologically. But we cannot make it conform to classical concepts of waves or particles or any hybrid combination of the two. Light exists in a category of its own minus a quantum entity that transcends the classical distinctions we use to organize our understanding of the world. Perhaps this transcendence is not a temporary limitation waiting to be overcome by future discoveries, but a permanent feature of how consciousness relates to quantum reality. The mystery persists in every beam of light that illuminates your world. The photons hitting your eyes right now to create the experience of vision exist in quantum superposition until they interact with the molecules in your retina and collapse into definite energy states that trigger neural responses. The sunlight streaming through your window, the glow from your computer screen, the reflection from every surface you see, mine is. All of it represents light, making the transition from quantum possibility to classical actuality through processes that physics can describe with incredible precision, but cannot explain at all. You are constantly witnessing wave-particle duality in action, but the transition from quantum to classical happens so rapidly and seamlessly that it remains invisible to direct observation. Perhaps that's the deepest lesson about light's dual nature. It might not be meant to be understood in any classical sense, only experienced and used and appreciated for the incredible complexity it makes possible. Wave-particle duality might be nature's way of demonstrating that reality operates according to principles that exceed human comprehension while still being accessible to human investigation and application. Light doesn't know what it is, because the question assumes categories that don't apply to quantum reality. But somehow, impossibly, this not knowing creates everything you see, enables everything you experience, and makes the entire visual world possible through mechanisms that work perfectly while remaining fundamentally mysterious. The equations describe it all with mathematical precision. The experiments confirm every prediction. The technologies prove that we can use these principles effectively. But the central question remains as unanswered today as it was a century ago. What is light actually doing when no one is looking? The answer might be that light isn't doing anything definite. It's existing in a state of quantum possibility that transcends classical description until measurement forces it to become something we can recognize and use. But we participate in creating what we observe without understanding how that participation works or why it should be necessary. The mystery of light's dual nature might be inseparable from the mystery of consciousness itself.